Welcome in the second morning of the Charm++ workshop. It gives me great pleasure to welcome Rajeev Thakur to the podium. Rajeev, probably best known for many of you now as the director for software technology for the Exascale computing project, which is the vehicle for the Department of Energy to build the next generation supercomputers that are going to set a new standard. Hopefully you'll hear something about that in a minute. I know Rajeev for many, many years. He graduated in around 95 from Syracuse. He has been at Argonne. At Argonne, he's a senior scientist. He's also a senior fellow of the Computation Institute at University of Chicago, and known to many of us for his efforts in MPI, MPICH, and MPI Forum, as well as for some of us more narrowly on a pretty important topic of input-output in the Romeo library associated with MPI as well. Without further ado, Rajeev.
Thanks, Sanjay, for the introduction and invitation to this workshop. I hear about this workshop every year, but I've never been able to actually make it here. So this is my first time, and I'm happy to be here. And I saw that it's the 15th annual workshop, which is amazing that it's been going on for 15 years. My talk is slightly different from other talks at this event, which are more Charm++ related, either users of Charm++ or those who are developing Charm++. This is about something related. It's the Exascale computing project that has been going on for a year or a little more, and you may have heard of, and more about the software technology aspect of it that I'm involved in. Let's see. Okay. So what is the Exascale computing project? It is a collaborative effort of two Department of Energy, US Department of Energy offices. One is the Office of Science, and the other is the National Nuclear Security Administration, known as NNSA. And it is part of the National Strategic Computing Initiative that was launched July of 2015, I think, which is getting close to 2 years. And one of the things in the NSCI was exascale computing. And ECP was established to accelerate the delivery of what we call a capable exascale computing platform. And I'll say in a minute what that means. That integrates hardware and software capability to deliver 50 times more performance than the nation's most powerful supercomputers in use today. And today refers to July of 2015, but I don't think things have changed too much in 2 years, at least in the US, in terms of supercomputer deployment. And ECP's work encompasses applications, system software, which is what we call software technology. And that's what I'm going to talk about. I'll talk about other aspects as well. There is some work in hardware technologies and architectures that's more in coordination with vendors. That's work done by the vendors. There is also some work in exascale systems, and also workforce development to meet the scientific and national security needs of the DOE. Starting late in 2015, but officially in 2016, ECP was initiated as a DOE Office of Science and NNSA partnership. And it uses DOE's formal project management practices and processes. So what that means is it is considered a large project, and DOE has many large projects in the sciences. These are experimental facilities for in physics and so forth. And they all follow a very well-defined process in terms of project management, and there are various review phases. There are critical decisions made in which the project is assessed and approved, and the next steps can happen. There's lots of milestone tracking and so forth. So all that is ECP falls under all of that. And that's what project means in DOE language, that all this project management comes into play there. And it is led by DOE labs, but executed in collaboration with universities and industry. And I'll talk more about that. The core ECP leadership team is from 6 labs. And they are, the project is led by, the project office is located at Oak Ridge, and the other labs are Argonne, Berkeley, Livermore, Los Alamos, Sandia. I hope I've covered all 6. I think so, yeah. And there are 17 DOE labs, by the way. You may not know, but most of the 17 are involved in it in some way, as well as many universities and companies. And the ECP also collaborates with the computing facilities that DOE has that operate the systems and that will deploy the Exascale systems. And I'll talk a little more about that as well. So what does a capable Exascale computing system mean in the ECP language? So a capable Exascale computing system requires an entire ecosystem that will deliver 50 times the performance of a 20 petaflop system roughly that we have in the US today, and running real applications, and I'll talk about some examples of applications, and delivering solutions that are not just faster, but also maybe higher quality, higher fidelity. There's some figure of merit involved. The 50x is not just speed, but the overall figure of merit has to be around 50x better than today. And it also operates within some power constraints of 20 to 30 megawatts. So it's not substantially higher than the power consumed by the most power consuming system of today. The system has to be sufficiently resilient, and we have set the resilience metric to what it is today, which is roughly 1 week, in the sense that you can run an application for a week at least before there is some failure. Often machines have a downtime, regularly scheduled downtime once a week for software upgrades and so forth. So they go down. But we want to continue to maintain that resiliency metric. And it includes a software stack that meets the needs of a wide range of applications. So it's, and we will see the set of applications we are considering as well. Okay. What are some of the challenges that need to be solved? And this is not something new. This is what people know already. One is the parallelism. An Exascale system will have maybe 100 times more parallelism than the 20 petaflops system. So that needs to be taken into account everywhere. The applications need to account for it. The software stack, programming models need to account for it, and so forth. The systems will have more complicated memory hierarchy and even a storage hierarchy. So we need to be able to use that efficiently. So you need software support, and the applications have to use it. Reliability, the resilience metric, so that needs to be taken care of at all levels. The hardware, the software, applications. If they get an error, they need to know what to do with it, and so forth. And energy consumption, which is not just a hardware issue, but there may be some support needed from software in terms of making sure that we don't consume too much power. So these are the kinds of issues that need to be taken care of or resolved. So ECP's plan involves a lot of co-design and integration among its 4 main focus areas, which are application, software, hardware, and Exascale systems, and we'll see more about this as I go along in my talk. So the current ECP plan of record, which is which was I think finalized last November, October-November timeframe last year, and it's still the plan of record today, is that it's a 7-year project that follows a co-design approach, running through 2023, and that last year is actually more of a scheduled contingency. So there is the funding in the last year. It's a carryover type of thing, And it would enable an initial exascale system based on an advanced architecture delivered in 2021. So this term advanced architecture was added to this plan in November, and the Secretary of Energy wanted that. What it means is that the vendors are encouraged to think beyond what they might have in the beyond the Coral and Aurora type of systems. They're encouraged to see what else they could do and provide a system in this time frame while still meeting the application needs and so forth. And enable capable exascale systems based on the ECP R&D delivered in 2022 and deployed in 2023. So there is one system in 2021 and one or more in 22 or 2023, depending on the budget. And one thing to note is that the acquisition and deployment of these systems is not part of the ECP project. That will be taken care of by the DOE facilities, like the leadership facility at Argonne or Oak Ridge, and the equivalent facilities at the NNSA labs. So it's part of their budget, and it's part of their normal, their procurement plans and so forth. The work ECP does is to enable them to be able to acquire a system at a reasonable price point and a power consumption point, and with software and applications that actually run and can take advantage of the system. So this is a high-level technical the project schedule. So the first 3 years of the project until about 2019 have there's application development work, which I'll talk about. There's work in software. There's work in hardware, which involves funding the vendors to sort of do things to accelerate their roadmap. Then there's sort of a phase shift at this point, because this work will continue in applications and software and in hardware, but by then the first system will be known. Right now we don't know what that first system is going to be, so we are not building software specifically for that system, or we're building it more generally for 2 or 3 possible systems that can happen. So in this second stage, there'll be more of a hardening of the software or tuning it for those platforms. There may be fewer projects than there are today, because we'll know more about what is actually being used and so forth. I'll talk more about that. There will be some NRE work. NRE stands for non-recurring engineering, and that is done typically in these big procurements, where along with the vendor contract, there's some amount of funding to do the one-time engineering work to deliver what is needed on that system, and that has both software and hardware components, and that is part of the ECP project. So there is some budget for the NRE aspect as well. Also, part of ECP is the test beds that are needed to do the application development work and the software work. So there'll be some test beds deployed at the DOE facilities, where all the project participants can run their code and test their platforms. And there are already a couple of these test beds. There is one at Argonne that is the precursor to their 2018 system, the Aurora system. It's like a one rack of it or so forth. And at Oak Ridge, similarly, there is a Summit Dev, which is the precursor to the Summit system, and a portion of this is a test bed for us. And this last, the things at the bottom, the site, this Exascale system and the site prep, that lies in the facilities space. So it's not part of ECP budget or the project as such, but we work closely with the facilities to make this all happen. Just a quick summary before I get into some details about this is what is the current project status. So last year, 22 applications projects were selected for funding, in addition to 4 projects that are already underway at the NNSA labs, and those are their classified codes, next generation versions, and those 4 are also considered part of ECP. There are 5 co-design centers have been selected for funding, 4 last year, and there was one smaller effort earlier this year, I think February-ish. Then there were 35 projects in software technology that were selected last year and announced just before the SC conference. And there are a similar number of them already underway at NNSA labs as part of their ATDM initiative, which I'll talk about in a little bit. So it's a bigger portfolio than that. And there were some, there was an RFP for vendors, a request for proposals that was called the Path Forward program, by which vendors had to submit their proposals to sort of accelerate things in their roadmap so that the systems could be delivered earlier and so forth. So those projects or the proposals, the final set has been selected and the negotiations are underway, and I think 2 or 3 of the contracts have been fully signed, but a couple of them are still to be signed. And in a few weeks that should be done and announced. There are many levels of approvals needed, even all the way in Washington and so forth. So that has taken some time, but the announcement should be sometime in the month of May. And ECP covers many institutions and many researchers. So there are the Confluence and Jira wiki, the Confluence wiki and the Jira project management system has around 800 accounts right now. So there are that many people using it, and it's all over the country. There are about 39 university partners involved and many labs, and there's an industry council as well, more as an advisory. It's an advisory body, and the industry council is the users of HPC, not the developers of HPC technology, but more the consumers of HPC technology. So it has United Technologies and General Electric and those kinds of companies. I may say a little more about that in the panel this afternoon. So this shows the leadership team. So Paul Messina is the project director, and he's at Argonne. Stephen Lee is the deputy director, and he's at Los Alamos. Stephen was a division leader for their computing division for many years, probably 15 years or so, before he's now full-time in the ECP project. In the 4 focus areas, the applications is led by Doug Cothey at Oak Ridge, and the deputy is Bert Still at Livermore. Software is I'm the lead, and Pat McCormick is the deputy at Los Alamos. In hardware, Jim Ang leads the hardware area, and he's from Sandia. And John Schalf from Berkeley is the deputy for hardware. And for the Exascale systems, Terry Quinn from Livermore is the director, and Susan Coughlin from Argonne is the deputy. And this has close connections with the facilities that the DOE runs, and they both come from the facility side as well. So they are our connection there. One more thing you can see is that each area has a person from the Office of Science side and from the NNSA side. So if it's led by an NNSA person, then the deputy is from Office of Science and so forth. Al Geist from Oak Ridge is the CTO, and Julia White is the integration manager. Integration is an important part of this. All the software stack needs to be integrated. The applications have to work with it and with the hardware and so forth. And Mike Bernhardt is the communications manager. Mike used to be at Intel earlier, and he used to put out something called the Exascale report, I think it was called. It was a newsletter about 4 or 5 years ago, and he was doing it for a couple of years, so you may know him from there. So this is the software technology area that I'll focus on. Being a project, it has also like a work breakdown structure. So these are things that projects need to have. And so each of those areas has sub boxes, which I won't get into. I'll talk only about the software part. So in software, we have programming. The different areas are programming models and runtimes, tools, math libraries, data management and workflows, data analytics and visualization, system software, resilience and integrity, co-design and integration. And one last thing was added is there's a potential software path forward to vendors if there is a budget for it and if there is a need for it. I'll talk about it in a little bit. And each of these areas has their own leads. And they are both technical leads, and they also have a project management role in making sure that the projects in that area are on track and are meeting their milestones and so forth. So you recognize many of the names here. They are fairly well known in their area. So I'm also doing double duty and leading the programming models area. Jeff Vedder from Oak Ridge is leading tools. Mike Haru from Sandia is leading the math libraries. Rob Ross from Argonne leads the data management and workflows area. Jim Aarons from Los Alamos is leading data analytics and visualization. Martin Schulz from Livermore is leading system software. Al Geist is leading the resilience and integrity. And co-design and integration is led by Rob Neely. And this is a very important area because all these projects in this set, which I'll get to, they need to work together and come together as a single stack. So all the interfaces need to be defined and work together. The testing and integration has to happen. So that's a very important area. I believe Rob was part of this group a long time ago, right? He was a student here, I think, in early 90s, and maybe one of the early developers of Charm or Charm++. What was it called at that time? Was it Charm++? Charm, right? So there are some. It's a small world.
Just making the transition to Charm++.
Yeah. Okay, so let me talk a little bit about the software technology focus area. So the goal of the software technology area is to build a comprehensive and coherent software stack that will enable the application developers to write their applications that are highly parallel, that scale to the full Exascale system. And they can also portably target diverse Exascale architectures. So one of our requirements is that the Exascale systems have, that get deployed have to be diverse. They have to be different, and the applications have to run portably on both. And there is a metric that gets tracked, that is the performance portability metric. So we have to write software and have them run on these systems without having lots of if-defs or writing a whole different code for the other system. So that's difficult. That's not easy. And the way we plan to do this is by extending current technologies to Exascale where possible, performing the R&D needed to come up with new approaches where necessary. And we also coordinate with vendor efforts. That is, we are not doing everything. There are things that vendors typically provide when you buy a machine. The machine comes with a file system. We are not building a file system. We're not building the basic operating system that's on the machine. We may be building some components that can be plugged in or that the vendors can leverage and add to their OS level work. But the majority of things that we are doing are things that sit on top of what the vendors provide. And even today, that is the story. The vendors don't provide the entire software environment. That comes from the labs or universities and other open source efforts. And we have to develop and deploy high quality and robust software products that are actually deployed and used. So it can't be just a prototype. This has to work in practice. So what are the vision and goals for the software stack? One is deliver and anticipate. So provide the foundational software and infrastructure to applications and facilities necessary for project success in the 21 to 23 time frame, while also pushing to innovate beyond that time frame. So what that means is that we want to both deliver a quality solution while also looking at what the applications might need in that time frame that they don't know today. We can't just meet their requirements that they say today, because they may not even know what is necessary in those systems. So we have to look at what's coming and make sure that we are covering those areas. The second one is collaborate. Is that there are so many pieces to this stack that there has to be some common infrastructure and APIs that they need to agree to so that everything works. And we are also encouraging the software projects to expose parts of their software or build APIs so that others can use it. There may be components that that are useful to others but are internal to many of these software packages, but that needs to be exposed. So that kind of activity is also going on. The third one is integrate. That is, we have to work with the vendors to provide a balanced offering between the lab or university developed open source projects, the vendor offered the proprietary software, and jointly developed solutions. By jointly, I mean there are some that are developed by universities and labs, and then the vendor takes that and tunes it and then provides it on their system and also provides the support and so forth. An example is MPI. There are also some math libraries that fall under that category, and there can be more. Then the next one is quality. That is, build production quality software that is easy to build. It's well tested, documented, and supported. Then we also have to prioritize, because there are many things that can be done. There are many things that are interesting, but we cannot do all of them. And I'll show you some examples about the number of software that is mentioned or used. So we have to prioritize. We have to focus on the ones that deal with scalability, or that deal with performance, or that need ECP to do something. So there is a constant looking at the whole set and prioritizing. And finally, also completeness, is that we perform a regular gap analysis to see what is missing based on all these criteria and the priorities. And also incorporate risk mitigation, which may involve a few competing approaches in areas that are high risk or that are critical. So we don't have too many of these, but for example, we have 2 efforts in MPI, but that is something that is needed on every system, and the vendors also depend on these open source projects, and they use the software produced there. And clearly, the software stack needs to integrate with both. There's a lot of integration work within the software stack, but it's also across other areas. So the applications need to use the new features or the new versions of the software. If they take it easy and they use the current software that is deployed, that doesn't help us, because the new software needs to be tested and debugged, and we need that feedback. So that level of integration is needed. We need to know what the vendors are doing. We need to know what's happening in those path forward projects that I said. And are there any surprises, or are there any changes that we need to be aware of, and take those into account into our software development. And similarly with the Exascale systems area. So where do the requirements for software technology come from, or how do we decide what projects we should work on or fund? There are many interesting topics that are worthy of doing and that can be pursued, but we cannot do all of them. We don't have the budget for all of them. So the way we select our projects or did the last round of selections is based on some requirements. One is what are the applications saying that they need, or they're using, or they plan to use. So an analysis of the software needs of the applications, and I have some examples of that. Also an inventory of the software environments at the major DOE facilities at those 6 labs. So last year we asked these facilities to give us an inventory or the set the software that is being used at those facilities, both for the current systems that they're running and for their next procurement in the next 2-3 years. So that's the Coral systems at Argonne and Oak Ridge, and the Apex at Berkeley and Los Alamos, and they have that information, and they have and they've given it to us. So there's and it's a pretty large set. So I'll show you that. Again, it's too large. The facilities require a lot of software because it's a production center, and we have to from that we have to see which parts are critical and essential for us to focus on and fund. Then what is the expected software environment on an Exascale system? Then what needs to be done beyond the software environment provided by vendors, and I'll say a little more about that as well. And then finally, what is needed to meet ECP's key performance parameters? So any project in DOE space has a set of key performance parameters that it needs to meet. And at the end of the project, these things get checked. And if it doesn't meet them, then the project is, it's not deemed to be successful. So some of the things that are in the KPPs are the number of applications that will scale and run on these systems. There is one on performance portability. There is one on power and something else. Now the exact numbers, that is how many apps or what the power should be, that is not set right now. That gets set a little later, I think around 2019. When the actual system is known and a little more is known about the platform. So right now we know the rough areas, but we don't know the exact numbers. But we have to keep that in mind as well. So just to show you an example of the application requirements. We've got these kinds of requirements. So this is an example of quad charts that the applications have put together, and this is an example of a subsurface simulator. And in this quadrant, it lists the software technologies. These are the codes that it uses, the languages, the programming models, the math libraries, this is the I/O and visualization libraries. And if you take another application, this is NW-Chem, then these are the languages, a different set of programming models, some different set of other libraries that it used. And if you look at the whole set, the entire set of applications, there are a large number of software that is mentioned there. I won't go through the whole list, but pretty much everything that you can think of gets mentioned somewhere or the other. And we can't support or fund all of these, so that's where the prioritization comes. Which of them are being used by multiple applications, or which are critical, or which could manage without our funding and so forth. Then we also have other data we looked at the 30 application proposals that came in last year, and just a simple keyword search to see what software was mentioned in which proposal and how many times. So MPI was mentioned in all 30 of the proposals, and then OpenMP in 27 of them, and then CUDA, HDF, and so on. And there are many down in this level mentioned in a few. So that's another data point. And of course, this was just a keyword search. We have to look at the context and look at how much they depend on any of this software and so forth. Then from the facilities, we've got some detailed information, and this is an example where they've given us information about they keep track of how many times libraries are linked on their systems, so they know that which is being used the most and so forth. So this is over some time frame, the libraries that were linked at NERSC. So there is MPICH, there is Darshan, which is an I/O instrumentation library, and so forth. And we've got similar data from Oak Ridge and others. So that's another, what happened here? Another input point. So this is the kind of requirements that we look at when we select the projects. So let me talk about the projects in the current set. So as I said, there were 35 software projects were selected last year, and the way that happened was there was an RFI, RFP process early last year. There was a request for information for like 3-page pre-proposals. It was a targeted RFI sent to people who develop software that runs on large systems. I was not part of the project at that time. I joined somewhere, I joined on the day the RFI responses were due. So the first task was to deal with all the 100 and something responses that came in, and then from that we selected a subset for full proposals, and then there were the final set of 35 that were announced in November. And as I said, there are some projects that have been ongoing at the NNSA labs for about 4 years now. It's their program called ATDM. You'll hear that acronym. It stands for Advanced Technology Development and Mitigation, and it is meant to sort of develop their next generation of application code. So there are some applications that are part of this ATDM program, and then the associated software technology needed for those applications and to advance it for the future. That's been going on for 3 years, but that is NNSA's contribution to ECP. So those projects are also part of ECP. So the overall set of projects is bigger. There's 65 or 66 projects. So I'm going to show you that, and we have a conceptual ECP software stack. I'm going to show you the set of projects, or actually the set of technology. This is not the names of all the projects, but names of some of the tools or the packages that are part of it. It's a large set because sometimes there is one project building many tools and so forth. So it's not a clear mapping. This includes the 35 announced last year plus the ATDM all in one. So in the area of programming models, we are supporting multiple programming models, not just MPI and plus OpenMP, and applications are encouraged to try some of the newer models as well. So there are two efforts in MPI. I have some more information on these programming models projects, since that's of interest to this group, and I'll get to that. But there are 2 projects in MPI. There is a large OpenMP effort. There is OpenACC is a smaller effort, and is actually part of this project here led by Jeff Vedder at Oak Ridge. There are 2 PGAS efforts, UPC++ and global arrays. There are 3 efforts in task-based models. There is the Parsec tasking model that at UTK, it's Jack Dongara's, and there is Legion led by Los Alamos. And Dharma is an ATDM funded project, and you know about it. I think it was presented yesterday. And then there is the Raja and Cocos efforts at Livermore and Sandia, which are more code transformation for performance portability. And there's quite a bit of application interest in these kinds of things. There is an ATDM project on tools for OpenMP, tools interface for OpenMP actually, and that's Martin Schulz effort. And there's another project on power steering. I'll talk more about it in a little bit. The math libraries again were selected based on what the applications are using, and these are all recognizable names. So many of these projects are about they're codes that already exist and are used, but they need to be taken to Exascale. So a lot of the work is that. So there are the usual dense linear algebra, sparse linear algebra, the PET-C tau, Trillinos. There is work on these are the sparse solvers. There is some other work at the NNSA labs and so forth. DTK is a tool for code coupling of multi-physics codes and so forth. There's quite a bit of interest in this. On the tool side, again, there are some tools that are well known. The HPC toolkit. There is some work in tau as part of this Proteus project. PAPI at UTK. Darshan is a tool for I/O characterization, and it runs on many systems. It's actually part of a project here, but I've listed it separately. There are efforts related to performance portability. There is ROSE. There is an auto-tuning effort led by Mary Hall at Utah, and Jeff Vetter has another project in that area. And there are some other tools efforts at Livermore. Martin Schulz leads them. That's the ATDM funded projects. And there's work in LLVM, and then the Fortran Flang LLVM work that is being done also as an ATDM project, but Los Alamos and Livermore are funding PGI to do that, and that's going to be open sourced pretty soon. So there will be an open source version of this Fortran LLVM this month or early next month. On the system software side, as I said, we're not building an operating system, but these are parts that add value over what the vendors are doing and can be plugged into vendor efforts. They're tightly coordinated with vendors. So there's some work in the global OS and global resource management. That's part of the Argo project led by Pete Beckman. It's a smaller effort on Q threads at Sandia. Flux is the is a scheduler or resource management work at Livermore. That's a follow-on to their what I'm forgetting the name for their current system. What's the current Livermore? I'm blanking on that name, but it's the follow-on to that. Then there are other projects. I think Spindle speeds up the applications that use dynamic loading or Python and so forth. And at the Node OS level, there's some work in Argo, and there is one ATDM project at Sandia. In the I/O space, I've kind of divided it into two, and some things are cross-listed. Let me talk about this first. On the data management, there are efforts in HDF, NetCDF, MPI/IO, RDOs, then checkpoint restart. There is one effort that is a combination of the SCR work at Livermore and the FTI work at Argonne. That's Frank Capello. So that's one project called Veloci. And Unify CR is a Livermore-led project that is building a sort of a user-level file system for burst buffers. These systems will have burst buffers, so that'll provide a way for users to get their code, to get their data out of the burst buffers easily. It's a user-level file system type thing. There are two relatively small efforts in compression. Easy is led by Frank Capello at Argonne, and ZFP by Peter Lindstrom at Livermore. Again, these plug into the I/O library, so they'll plug into HDF or RDOs or NetCDF, and so the users can transparently get the benefits of compression. And there is some work in I/O services to help build I/O libraries and other ATDM efforts in data management. Then on the burst buffer side, there are some cross-listed projects. The checkpoint restart and the Unify and the Veloci efforts, they also deal with burst buffers, so they are listed there. And there is one project led by Mike Lang at Los Alamos, and it involves Oak Ridge and Livermore. I think Maya Gokhale from Livermore is an API and library for managing the complex memory hierarchy. So that's a new effort. So that's not existing code, but we felt that that's something that is needed for these exascale systems. Then there are two cross-cutting areas: workflows and resilience. And before that, let me just cover. The applications and code design is a separate area, so it's just here to show where these boxes lie relative to applications. In the visualization and data analytics, there is work on taking visit and paraview to Exascale, and VTKM is improved algorithms that are used by these visualization libraries. So in the area of workflows, there were like 4 proposals in workflows, but we decided to defer any decision on them because we didn't have a good understanding of what the applications need in the area of workflows. It's clearly an important area, and it's something that is needed, but it was not clear what tool we should provide that they will actually use, or they want to roll something on their own. So we decided to defer any decision. There is some existing work at Livermore, part of an ATDM project, so that's what is listed there. But in last year's, the RFI, RFP, we ended up not selecting. We are doing a survey of applications right now to understand their requirements. It's not an easy answer, I feel. Workflows it's a bit complicated. Then similarly, in the area of resilience, the last year's RFI did not ask for proposals on that topic because there was a research program that had just been initiated by the DOE OSCAR office in the area of resilience. So we wanted to see what the progress among projects in those areas, and also understand what is really needed for resilience on exascale systems. There is some existing work as part of ATDM at Los Alamos in the area of fault modeling and fault injection and so forth. And of course, these checkpoint restart libraries also have use in this case, so they're just listed there. I think I've covered everything, and we can talk later. I just had one slide each on some of the programming models projects, since that's of interest here. so as I said, we have two MPI efforts, and we selected two for a couple of reasons. One is that both are used and even by vendors. So there are vendors who take these open source developed effort and tune them for their platforms. So there's the MPICH and the Open MPI, and it's also a risk reduction method. So this is led by Pawan, and Mark Sneer is involved, and some students from Illinois are involved. In fact, they were at Argonne yesterday for a project meeting. I ran into Mark at Argonne. I think we both drove back to Champaign around the same time. So this is improvements to the MPICH implementation in the area of threads, heterogeneous memory, topology-aware communication, fault tolerance. New features that will be added to MPI. So they're all engaged in the MPI forum and making sure that the MPI standard itself has the features in it that are needed for the future platforms, and technology transfer to vendors. They have code hackathons with vendors regularly, with Intel and Mellanox and others. There was one I think just last week in Austin, and they coordinate with the Open MPI and Open MP efforts. There's the Open MPI project led by David Bernholt. And it involves Los Alamos, Livermore, Sandia, and also UTK. And this has similar improvements to Open MPI for Exascale, and also they are active in the MPI forum, and they are also involved in the vendor efforts. There is an Open MP project led by Barbara Chapman, and it involves Argonne, Livermore, Oak Ridge, Rice, and I think Sanjay is a collaborator but not funded. In the final, the budget scenario, all projects had to take a cut in the budget, so there were it resulted in some unfunded collaborators. So this enhances OpenMP using LLVM and lightweight threading. There are enhancements to the OpenMP standard. OpenMP MPI interoperability is important, and working with applications to use the newer features of OpenMP and also using them in a way that they'll get performance. So it's you can use OpenMP easily, and you may not get the performance you were hoping for. So there is some additional work needed, and these are the experts. So there's a lot of application interaction there. Then there is a PGAS effort, that is the UPC++ GasNet from LBNL, and there is some application usage here. There is the Legion runtime uses it, and the applications that are using Legion will use it. There is a co-design center on AMR that is using it. There is a bio application also from Berkeley that is using it. So these are enhancing UPC++ for Exascale. Similarly, there is a smaller effort on global arrays. The NWChem application relies on global arrays, so this takes global arrays to Exascale. It's also used in another grid pack code related to the electricity grid type of applications. Then on the tasking methods, there is one from UTK. This is Parsec. It's a runtime for dynamic execution on heterogeneous systems, and they use it to build their math libraries also. So the Plasma, Magma, those efforts are built on top of this framework. They've also built some domain-specific languages on top of this. Yeah, and it's used in dPlasma, as I said. There's a prototype of NWChem that uses it. There is work on the Legion programming system. It's led by Los Alamos, and it has partners at Stanford and Argonne and someone at NVIDIA. So that's a high-level task-based programming model, and with a runtime system that automates the mapping and scheduling of tasks and data movement. And it is used in the S3D combustion app. That's one of the ECP apps. It's being used in the next generation code at Los Alamos and others. Dharma, there was a talk yesterday on Dharma. So this is an ATDM project, and Janine Bennett is the lead, and it provides like a portability layer on top of various runtimes, and I think their first target is Charm++, so this has strong ties to Charm++. Raja and Kokos are efforts at Livermore and Sandia, and they are sort of abstraction layers that try to encapsulate they use advanced C++ to hide the architectural details and portability issues. So you can write your code once and then have it translated for different architectures. And the applications are quite interested in this. Cocos has some tutorials, and there's a Cocos training event in May that anyone can participate in. I think it's in Santa Fe, and I can give you more information. You'll find it online as well. There is a runtime library for application level power steering by Martin Schulz, and it's a job level power management system that can optimize performance under power or energy constraints, and it uses this Intel's global energy optimization library. So they have collaboration with Intel, but something like this would be useful to meet the power requirements. There's a tools interface for OpenMP. That's ATDM effort that's similar to the tools interface for MPI, but applied to OpenMP. I'm going a little quickly because we're getting to close to the 10 o'clock. Yeah, it's 9:55. There was a RFI issued to vendors in February with responses due by March. And they have come in. The reason I put this up is it's not that you have to respond to it, but it has some information that if you read it, I think you'll learn something. It's only about 5-6 pages. So it asks the vendors for information on their hardware and software plans up to 2024, and to identify potential gaps that might need funding. And it has some details about the procurement plans of the DOE facilities up to 2025, and the kinds of questions that get asked in this kind of RFI. But the details that are asked there I think they're interesting if you have not been exposed to this. So that's why I put this up, and you can get it from that website. The next step for software is a gap analysis. That is, we need to we're having discussions with a number of folks at the vendors, the facilities, applications, and also reading the responses to that RFI that I just mentioned, and doing a gap analysis to see what is missing, what is currently covered by the set of projects I talked about, and what is it that the vendors are doing, and what is it that others may be doing and might be available, and what are the missing pieces that may need some future funding. And some examples are workflows. There is software for data analytics type applications. So that's a big hole, the second bullet. What we are covering is mostly the simulation type of applications. And if we have a newer set of codes that are more data analytics oriented, and then we'll need to support them in some way. And there are other topics as well. And based on what comes out of this, and depending on the funding, our budgets. What we know are from last year. We don't know what the current administration's budget is. That we'll know more about it in the next couple of months, and based on that, we hope to have another of the RFI, RFP, targeted to covering the gaps that were found. I had some slides on applications and co-design, which I think I'll go through quickly in the interest of time. So there were 15 applications selected last year, and 7 seed efforts, that is smaller funded. So that comes to a total of 22. So there's one in nuclear energy. There is a climate application, the ACME project. There are 2 in chemistry. One is the NW Chem, and one is games, led by Mark Gordon at Iowa. There's one on wind energy. There is one on combustion, led by Sandia. So these are many of these are big efforts, having multiple partners, at labs and universities. They're led by a lab, but they have many partners. There's material science. There is Lattice QCD in nuclear physics, nuclear materials. There are 2. I think there are 2 projects related to accelerator physics, material science, fusion. I think it's PPPL led. There is one on additive manufacturing, led at Oak Ridge. Cosmology is the hack code, Salman Habib with many partners. There is one code on cancer, which is different. It actually uses machine learning and so forth. So this is the one code that is a bit different than others. There is a seismic code, carbon capture. There is a small effort on urban systems. This is a seed project led by Charlie Catlett. There's again a seed effort in metagenomics. Astrophysics is led by Dan Casson at Berkeley, and one on the power grid. And if you look at the motifs or the algorithms that are covered in these projects, this is a list of motifs that comes from the Berkeley set of motifs. This set just shows that each of these applications cover many of these motifs. So they're fairly serious applications, serious codes so the Exascale systems will need to be able to support all of these, and our software would need to be able to support all of these kinds of motifs and serious codes. There are also 5 co-design centers that are supposed to sort of work with these motifs and build their next generation. And co-design involves working with both the apps and the vendors and with the software to make sure that these kinds of algorithms are enhanced or tuned for the next generation system. So there is one co-design center. This is for online data analysis and reduction, led by Ian Foster at Argonne and with many partners. There is an AMR center led by Berkeley with many partners. There is another one it's on unstructured meshes and spectral methods, finite element methods, led out of Livermore with partners including Paul Fisher out here at Illinois. There is another center on the particle-based methods, and there's a new one started just 2 months ago. It's a small one. It's on graph-based methods, probably useful for future applications in data analytics. Some of the challenges on these applications face are programming models, which one to use, how to use, and so forth, how to achieve performance portability, how to couple the multiphysics codes, and these are common to many applications. On the hardware side, there are 2 efforts. One is the Path Forward program, which funds vendors to accelerate their roadmap, and the other is a relatively smaller effort. It's called Design Space Evaluation, which is there are teams at the labs that use hardware evaluation tools or simulators or machine models to sort of evaluate what these vendors are doing and provide them feedback. And this is what this graph shows that what the Path Forward effort is supposed to do. It kind of accelerates the vendor roadmap. So instead of being on that pink line, it provides a higher level of computing capability with their investments. I'll skip the systems acquisition slide because the facilities are involved in the systems acquisition. We are kind of helping them in that. One last slide on what ECP is addressing partially or not at all is this convergence of simulation and data analytics is only partial, and we'd like to do more of it if there is funding, and that remains to be seen. Then things like post-Moore's law technologies are not in scope of ECP, but they need to be worked on for beyond Exascale. And basic research in many areas is also not really in scope because the research programs at the DOE, OSCAR, or NSF could fund them. For example, new programming models, and the time frame is too short to do that as part of ECP, but it can be investigated as part of a research effort. Planned outcomes, I think I've already covered this. And as the first system in 2021 running applications on top of the ECP software stack and so forth, and 1 or more systems in 2023. And one last slide is just a plug for a conference this year at Argonne that I'm involved in, and it has some connections here since it is MPI related. It's the Euro MPI conference, which is held in Europe every year, is being held in the US this year at Argonne. It has been held in Japan once, so there is some precedence. Although that's a picture of Chicago, the meeting is actually at Argonne in our building there. Pawan is the general chair, and Bill Gropp and I are the program chairs. Papers are due in May 1st, but there's likely to be a few days extension because the cluster deadline is also May 1st, and we don't want to clash with them, so there will be a few days extension. There are also many good workshops planned, and there's one on 25 years of MPI. So this is the 25th anniversary or MPI. So Rusty Lusk and Jesper Larsen Traff are putting together this workshop. They're getting many people who are involved in the original MPI from the early days, like Bill will be there, Jack Dongara, Tony Hay, and others from that time. So that will be an interesting event. There are other good workshops on resilience and other things. So try to attend and submit papers. And yeah, questions?
So you mentioned software helping manage power requirements, probably based on a talk you heard yesterday. What about software helping with reliability requirements? I mean, thinking about Charm++ again, and
yeah, so there is room for that, and right now I think that is one of the areas like workflows where we have a relatively smaller effort. Currently, it's mainly checkpoint restart and more efficient and scalable checkpoint restart. And that was because there were some other efforts that were just started at the time when we were working on these plans, funded by the Oscar research side. So there were other efforts like the containment domains and other. So we wanted to see the progress over there and also identify our needs from the other side and see what the vendors are saying and how bad of a problem it is and what needs to be done before making the next step. So that could be a part of our gap and future efforts. There could be room for something like Charm++ as well.
Yeah, there has been a lot of discussion that MPI may not be the programming model, if you want, or the way we are going to write libraries for Exascale, and that maybe task-based system will be the solution, like maybe Charm++. So is ECP going to address some of that? Is there research to try to answer that question?
Yeah, so we don't have a good answer. The apps are still they're still using MPI. They're using others as well. So it's going to be a combination of it. There will be some applications that will use probably more of the other models, and I think there are some applications whose by the nature of their codes, maybe the MPI and MPI plus OpenMP might be enough for them. So that's why in our programming models box, we're not prescribing any one thing. We want to let the applications pick their model and go from there. And at the same time, we are encouraging them to try the new things, so that many of them have been just using MPI in the past, and we want them to go beyond that. But I don't think MPI will not exist or will not be used. I think it will still be used in combination, in conjunction with other things. Yeah.
So that's an incredible number of moving parts in this project. I was just wondering, what do you feel are sort of the areas of highest risk to the overall success of the project?
Yeah, so the risk is is this number of moving parts. It is their integration. The other risks are not knowing what the actual system is going to be. That that gets decided so late that in Japan, for example, they kind of already know their one system, and so they can build the software for that. Here we have to build software for any possible system, and even any number of applications. The number of applications is also quite a bit, and if it grows, then there will be more applications to support. So the risk is the space is too large. So
when do you expect to be able to narrow that space down?
So in a year or two, then we'll be closer to the system, knowing what the system is, and we may be closer to knowing what among the applications there may be a few that will be the more critical ones, and that will be counted towards the KPPs and so forth. So we need to make sure that those get fully supported. A bigger risk is also the budget. If the new guidance we get is lower, then some things come off this just because we can't afford them.
So I have a comment and a question.
Yeah.
The comment is, Maria's question about task-based runtimes. And in fact, one answer might be, task-based runtimes will be covered because there'll be task in OpenMP and there'll be all these UTK things and so on.
Yeah.
But the point I want to just make is that there is across node, there is multi-node adaptivity. Job level within job, but across nodes adaptivity is not addressed by most of these within node COCOs, Raja, whatever, all these other things. That's so I think that's a gap. Whether that gap is actually seen by applications is another question. The question I had was about applications. A risk seems to me that not enough applications come to the Exascale. How are you assessing? How are you seeing that issue?
Yeah, that is true. So when the applications went through their RFI, RFP process, their first round had some 128 responses or some large number of responses. So there are many applications wanting to, they may not be ready for it and so forth. So there's need for training for one. And so one of the things that is part of the thing, application portfolio is training and workforce development. I think it's a topic of our panel also in the afternoon somewhat, is how to get more codes. It's about the missing middle, but even at the Exascale level, it is a challenge because these systems are, not everyone has access to these big systems as well. We at the big universities and the big labs have it, but others don't have it. That's another issue.
Okay.
I guess it goes back to the budget, but of the 22 applications you mentioned, I noticed a lot of them were climate related.
Well, there was one climate, the ACME, which...
climate or alternative energy.
Carbon
sequestration.
Yeah.
It seems like a lot of that could be at risk.
It could be, it could be. Some of them might be smaller efforts also. That mix has some seed-funded projects and the full projects. I'm forgetting which ones are the seed ones and the full ones. I think the ACME was a full one, but there are. But yeah, anything can happen.
All right. Thank you, Rajeev. And let's stop here.